Ever wondered how to find the slope of the inverse sine function at any point? The answer is this beautiful formula. The derivative of inverse sine x equals 1 over the square root of 1 minus x squared. But what does this actually mean? Here's the inverse sine function and its derivative side by side. Notice how the derivative shoots up to infinity as x approaches plus or minus 1. In the next few minutes, I'll show you exactly how to derive this formula step by step using implicit differentiation. To understand the inverse sine function, we first need to look at the regular sine function. Here's the graph of y equals sine x, which you're probably familiar with. Now here's the key insight. If we want to create an inverse function, we need the original function to be 1 to 1. But notice that sine x repeats its values infinitely. For example, sine of 0, sine of pi, and sine of 2 pi all equal 0. To fix this problem, we restrict the domain of sine to the interval from negative pi over 2 to pi over 2. In this restricted domain, sine is 1 to 1, meaning each y value corresponds to exactly one x value. Now we can create the inverse function. The inverse sine, written as sine to the negative 1 x or arcsin x, is the function that undoes what sine does. Here's the graph of y equals sine inverse x, also written as arcsin x. This function takes a number between negative 1 and 1 and gives you back the angle whose sine is that number. Let me show you what this means with a specific example. If we want to find sine inverse of 1/2, we're asking, what angle has a sine of 1/2? Now let's clearly define the domain and range of the inverse sine function. This is crucial information you'll need for calculus. The domain of sine inverse x is the closed interval from negative 1 to 1. This makes sense because the sine function only outputs values between negative 1 and 1. The range of sine inverse x is from negative pi over 2 to pi over 2. These are exactly the angles from our restricted domain of the original sine function. Remember, sine inverse of x gives you the angle whose sine is x. This angle will always be between negative pi over 2 and pi over 2 radians. Understanding this foundation is essential because when we take the derivative of inverse sine, we'll need to work within these domain and range restrictions. Now we arrive at the key result. The derivative of inverse sine x has a specific formula that we need to understand completely. This formula tells us that the derivative of inverse sine x equals 1 divided by the square root of 1 minus x squared. But there's an important restriction we must understand. The crucial point is the domain restriction. This formula is only valid when x is strictly between negative 1 and positive 1. We write this as an open interval. Notice that we use an open interval, excluding the endpoints negative 1 and positive 1. This is because the derivative approaches infinity as x approaches these values. So remember, the derivative of inverse sine x equals 1 over the square root of 1 minus x squared. And this formula works for all x values strictly between negative 1 and positive 1. Now we'll derive the formula for the derivative of inverse sine using implicit differentiation. This method reveals exactly why the formula works and gives us deep insight into the relationship between inverse functions and their derivatives. Step 1. We start by letting y equal the inverse sine of x. This is our fundamental setup that allows us to work with the inverse function relationship. Step 2. Since y equals inverse sine of x, we can rewrite this relationship as sine of y equals x. This transforms our inverse function into a regular trigonometric equation that we can differentiate. Step 3. Now we differentiate both sides with respect to x. The left side gives us cosine y times dy dx using the chain rule, while the right side simply gives us 1. Step 4. We solve for dy dx by dividing both sides by cosine y. This isolates our derivative on the left side, giving us dy dx equals 1 over cosine y. Step 5. Here's the key insight. We use the Pythagorean identity to express cosine y in terms of x. Since cosine squared y plus sine squared y equals 1, we get cosine y equals the square root of 1 minus sine squared y, which equals the square root of 1 minus x squared. Step 6. Finally, we substitute our expression for cosine y back into our derivative formula. This gives us our final result. The derivative of inverse sine x equals 1 over the square root of 1 minus x squared. This derivation shows us exactly why the derivative formula works. The implicit differentiation method reveals the deep connection between inverse functions and their derivatives, giving us both the result and the mathematical reasoning behind it. Now we'll work through our first example to see how to apply the derivative formula for inverse sine. We need to find the derivative of sine inverse of 2x. Step 1. We identify our inner function u equals 2x and its derivative du dx equals 2. This is crucial for applying the chain rule correctly. Now we substitute these values into our derivative formula. We substitute u equals 2x into the formula. The derivative becomes 1 over the square root of 1 minus 2x squared, all multiplied by 2. Step 3. We simplify the expression. 2x squared becomes 4x squared, and we move the factor of 2 to the numerator, giving us 2 over the square root of 1 minus 4x squared. Finally, we must state the domain restriction. For the square root to be defined, we need 1 minus 4x squared to be positive. This gives us the restriction that x must be between negative 1/2 and positive 1/2. Our complete answer is 2 over the square root of 1 minus 4x squared, valid for x between negative 1/2 and positive 1/2. This demonstrates how the chain rule works with inverse trigonometric functions. Now we'll tackle a more challenging example that requires the chain rule. We need to find the derivative of sine inverse of x squared. First, we identify this as a composition of functions. The outer function is sine inverse of u, and the inner function is u equals x squared. Remember, the chain rule states that the derivative of a composite function equals the derivative of the outer function times the derivative of the inner function. Now let's apply this step by step. We apply our derivative formula for sine inverse. The derivative of sine inverse of u is 1 over square root of 1 minus u squared times the derivative of u. The derivative of x squared is simply 2x. Now we substitute 2x for the derivative of the inner function. Simplifying, we get 2x over the square root of 1 minus x to the 4th power. Now we need to consider the domain restrictions. For this derivative to exist, we need 1 minus x to the 4th to be positive. This means x to the 4th must be less than 1, giving us the domain negative 1 is less than x is less than 1. A common mistake is forgetting to multiply by the derivative of the inner function. Without the chain rule, you'd get an incorrect answer. So our complete answer is 2x over the square root of 1 minus x to the 4th, valid for x between negative 1 and positive 1. Now we'll see how the derivative of inverse sine appears in real physics problems. Specifically, we'll explore how it helps us find optimal launch angles for projectile motion. Imagine we have a cannon that needs to hit a target 90 meters away. The question is, what launch angle will give us the maximum range for a given initial velocity? The projectile follows a parabolic path, and the range depends on the launch angle theta and initial velocity. The range formula for projectile motion is r equals v0 squared sine of 2 theta divided by g. Here r is the range, v0 is initial velocity, theta is the launch angle, and g is gravitational acceleration. Here's our specific problem. We know the target is 90 meters away. Our cannon has an initial velocity of 35 meters per second, and we need to find the optimal launch angle. We'll solve this step by step, and you'll see exactly where the inverse sine derivative comes into play. Step 1. We substitute our known values into the range formula. 90 equals 35 squared times sine of 2 theta divided by 9.8. This simplifies to 90 equals 1225 sine of 2 theta divided by 9.8. Step 2. We multiply both sides by 9.8 to get 882 equals 1225 sine of 2 theta. Dividing both sides by 1225 gives us sine of 2 theta equals 0.720. Step 3. Now we need to find the angle whose sine is 0.70. This is exactly where we use the inverse sine function. We have 2 theta equals inverse sine of 0.720. Using a calculator, inverse sine of 0.720 equals 46.05 degrees. Since this is 2 theta, we divide by 2 to get theta equals 23.03 degrees. This is our optimal launch angle. The derivative of inverse sine that we learned earlier tells us how sensitive this optimal angle is to small changes in our target distance or initial velocity. This makes it invaluable for precision calculations in engineering and physics. Here's our final result. A launch angle of 23 degrees gives us the optimal trajectory to hit our target at 90 meters. This demonstrates the practical power of inverse trigonometric functions in solving real-world physics problems. Perfect. You've now mastered the derivative of inverse sine. Let's quickly recap what we've learned and explore where to go next in your calculus journey. Here's our key result. The derivative of inverse sine of x equals 1 over the square root of 1 minus x squared. This elegant formula works for all x values between -1 and +1. We derived this using implicit differentiation. Starting with y equals inverse sine of x, we rewrote it as sine y equals x, then differentiated both sides to get our result. Now that you understand this fundamental concept, it's time to practice and explore related topics. The best way to master this topic is through practice. Try more chain rule examples, work with composite functions, and always remember those domain restrictions. Ready for more? Explore the derivatives of inverse cosine and inverse tangent, discover applications in physics and engineering, or dive into integration techniques with inverse trigonometric functions. Before you go, I'd love your support and feedback. If this video helped you understand the derivative of inverse sine, please give it a thumbs up. Subscribe for more calculus tutorials, and let me know in the comments what topic you'd like me to cover next. Thanks for watching, and keep practicing your calculus.